We are now in 2C, where we would like to find the moment generating function of S. Now there is actually an interesting thing here if we think about S, because S is defined as the sum of observed ladder heights. The sum of observed ladder heights can be used to describe the event of ruin, in the sense that if the total observed ladder heights exceed the initial capital, then ruin occurs. So if we can tell something about the distribution of S, then we're also able to talk about the probability of ruin. For the moment generating function of S, we will need to know something about the distribution of K and the distribution of L. And fortunately, we know both of these from the previous exercises. So now let's get started. What we want to do is we want to find the moment generating function of S. We evaluate that in alpha for some real valued alpha. The definition of this is the mean value of e to the alpha s. And if you try to plug in the expression for s, then you can see that we get quite uncomfortable quite early, because you both have a k up here and loads of li's, and you kind of want to tackle them one at a time. So one of the things that we can do is use the tower property, as we have done tons of times before. And what we will do is we will condition on k. So we will take this condition on k, and then we take the mean value outside. Okay, if we look at this expression, then what can we do? Well, the outer expectation here is in fact just an expectation of something that's a function of k. In fact, you may kind of think of it as the mean value of some function of k. And we know that k is a discrete random variable taking values 0, 1, 2, 3, 4, and so on. So in order to find this expectation, you may just sum up over all the different values that this function takes and multiply by the probability that k will take exactly that value. So just from the pure definition of expectation, what we get now is the sum from 0 to infinity of the probability of k attaining the value j, multiplied by the value of this conditional expectation, where instead of k, we just plug in the value j, since we condition on k being equal to j. The nice thing here that we may note is now that the li's are in fact independent of k. And because they are so, we can remove the condition here. Also, let us just plug in the probability that k is equal to j using the probability function that we found before. Then what we get is this. Note that what we're taking is the mean value of e to the alpha L1 multiplied e to the alpha L2 multiplied by e to the alpha L3, and so on. Now, what do we know about the li's? Well, the li's are IID, so they're independent, which allows us to take the mean value inside the product, and they are identically distributed, which then tells us the product of j identically distributed, the product of the mean of j identically distributed variables is just the same as taking that mean and taking the jth power. So since the li are IID, and in the meantime we can also just take the 1 minus lambda divided by theta c outside, since the li are IID, we can take the mean of e to the alpha L1 and then take that to the jth power. Now let us try to notice what it is we have here. What we actually have is the moment generating function of L1. So it can be very useful to calculate that. Or if you want, you can also cheat like I did and Google it, or just memorize it. And if you don't have it memorized and you don't have access to Google, then you may calculate this moment generating function as the integral of e to the alpha x multiplied by the density of L1, which is given as such. Now that we have an expression for the moment generating function here, let us plug that in and try to calculate. So we have things to the jth power. You have lambda divided by theta c, and here you have theta divided by theta minus alpha. Theta and theta cancel, resulting in lambda divided by theta minus alpha c multiplied by j. Now, what we have here, is this working? What we have here is in fact also what we call a geometric series. It is a geometric series which converges as long as the thing inside is numerically smaller than 1. And in that case, we'll have a geometric series which takes the value 1 divided by 1 minus whatever is inside here. Our problem now mainly is we have to require that this lambda divided by theta minus alpha c is indeed numerically smaller than 1. Let us just assume that for a moment, because in that case, what we can do is use the formula for a geometric series and write this series as 1 divided by whatever is inside, 1 divided by 1 minus whatever is inside there. And we may rewrite that if we consider the first fraction, that is the same as theta c minus lambda divided as a whole by theta c. And you can actually see that I've gone ahead and done some of the calculations here already. So basically, you put this inside the same fraction, and then you notice that the denominator theta minus alpha c down there can be used in the 1 as well, and then you flip the fraction, and then you get what I get here. And if you then let the c's cancel and multiply the theta inside the parenthesis, then what we have is this expression. Now note that this comes with a caveat. The moment generating function for s is only finite if this sum is finite. And that requires this thing inside here to be numerically smaller than 1. And if it isn't, well then the moment generating function is infinite. So let us take a closer look at the condition that whatever is inside here should be numerically smaller than 1.